Hi, today we are going to talk about Bleichenbacher attack. It is also called a million message attack. It took the advantage of the flaws within the PKCS hash one function to gradually reveal the content of an RSA encrypted message. The core of the Bleichenbacher attack relies on an oracle, which is a system which can tell if provided with a sequence of bytes of a particular length of an encrypted message and whether the decryption would yield something which has proper padding format or not. And the properly padded PKCS hash 1 message has the following format. It has first two bytes as 00 and 02, and then it has some non-zero bytes which is the padding, and then it has 00, and then comes our message. So this is the proper format for a properly padded PKCS hash 1 message. So for simulating the Bleichenbacher attack, we are doing the following operations. So if y is equal to the encrypted message, we do two operations. First, we will query the oracle, the padding oracle, to know whether our message is falling in the properly padded format or not. And then we will be using the RSA's multiplication property, the modulus operations multiplications property, such that we are finding y dash equal to y e of s mod n, which is also having a proper padding format. So before going into the code, we can observe the following. K is the size of the RSA modulus, and that is 128 bytes, and we are setting the value of b as b equal to 2 raised to k minus 16, and we know that this is 1024 bytes long, starting with 0002. So therefore our message will be falling in the interval 2b 3b minus 1. So if m0 is the correctly padded plain text, it belongs to the interval 2b 3b minus 1. Now, so the process will be like, we will be finding an m1, like I said before. We are finding y dash y e of s mod n here. Similarly, we will be finding an m1 m0 s1 mod n by trying out different values for this s1, such that m1 will result into a properly padded message. And if it is properly padded message, we know that it will fall in this range to be 3b minus 1. So by this you can write m1 is m0 s1 minus rn for some positive integer r, and this value of r is nothing but the number of times we have to subtract n, so that it will go back to our previous range 0 to n minus 1. So from this equation we get the following: m0 s1 is equal to m1 plus rn. From that we can write m0 as m1 plus rn by s1. So using this you can narrow down the range of the m0 like this. We can substitute this here, so we can make it like, you narrow down the range of the message to b plus rn by s1 and 3b minus 1 plus rn by s1. So like this we narrow down the range of m0. m0 means our message. So we know that value of r is unknown, but only thing we can do to this r is we can limit the value of r based on the fact that both m0 and m1 are falling in the category 2b 3b minus 1. So the range of r can be defined as from 2b s1 minus 3b plus 1 by n, and 3b minus 1 into s1 minus 2b by n. So this will be the range of r from this r which we can observe from this. So now about the initial value of s1, what should be the value of s1, and from this one we know that from this range of R, we know that R is less than 3bs1 by n. So when you observe, for this value to become 1, this S1, if S1 is substituted with n by 3b, we can see that this whole value becomes 1. So suppose we take a value R less than 1, then that means R is 0, since R is an integer. So if R is 0, that means the equation we found above, like m1 equal to m0 s1 minus rn, in this rn, this part will become 0, so we will be getting m1 is equal to m0 s1. So if that is the case, then smallest value possible for s1 is 2. So if we substitute that, you can see that 2 into, and the smallest possible value of m0 is 2b. So you will be getting that m1 should be greater than or equal to 4b. But from this we can understand that this is not coming in the range 2b 3b minus 1. So we understood that R should be taken greater than or equal to R should be taken greater than or equal to 1. So from that we can take the value of S1 as n by 3b. Now we will be using a binary search with we will be using a binary search optimization for our code. It is like we will be finding the value of S1 by iterating such that we will be getting an message which will be having only finally will be reaching to one residual interval. And in this code I have a message which will be giving us only one residual interval, and that interval will be so this is the method to be so SI, you know the value of SI is 2b plus Rn by m naught, like the range of SI is from 2b plus Rn by m naught to 3b minus 1 plus Rn by m naught. So let's take AB, like m0 is in AB, that is the range of the message. From that you can limit the search space for SI. So here we are checking the whole space. So we can, to like each time you find the new range, you can limit the search space of SI like this. You can take 2b plus Rn by B, 3b minus 1 plus Rn by A as the new as the new range of SI, so such that we are limiting the space for each of the intervals. So from this you can observe that R should be greater than or equal to twice BSI minus 1 minus 2b by n. So from the should be taken like that, then only we will be obtaining that twice the SI minus 1 is less than SI. So we are narrowing down the range. So we will be taking R as twice BSI minus 1 minus 2b by n as the initial value for that case. So we'll observe the code now, and in my code this part is to decode the message from H to R text form ASCII format. Then here is my padding oracle implementation. As I told here, we will be implementing it as S of m. So this is S of function here. It is just checking whether my first 4 bytes as 0002 or not, and if it is not, then we are returning false. Otherwise we are entering here, and here we are checking after 4 if there is any 00 coming in the string. If it is present, that means it is in proper padding format and it will return true, otherwise it will return false. Now these are the functions for implementing ceil and floor functions, and n is our modulus value, and b is equal to 2 raised to k minus 16, but you know that k is 1024. So 1024 minus 16 will give you 1008. So the value of b is 2 raised to 1008. So this is my initial message. Which is the H format for the message GNU, which I'll be showing while running the code. So Okay, so now we'll be, now this is the code for searching, this is for S1. So searching for S1. Okay, sorry, searching for M1. S1 and M1. First we'll be setting the value of S1 here, and S1, as I have told here, we'll be taking n by 3b initially, so that is what is taken here. Now we are finding a new M1 such that it is in properly padded format or not. So that checking is happening in this if it is in proper padding format, it will come out of this loop, and you will be getting the I am printing the iteration count and that particular S1. So this way I am getting the S1 value here. So now we will be using this in to narrow down our the interval of m naught. So that is what is being done here. Here we are taking the new interval a, like new lower range, and new a and new b. New a is our new lower bound, and new b is our new upper bound. So new a will be taken as the maximum of the original. A is like our original one, like see here 2b, and a is 2b and b is 3b minus 1. So we will be taking the maximum value of the old one and the newly found out, which newly found interval is like this: 2b plus rn by s1 and 3b minus 1 plus rn by s1, based on the value of m1 you got. That is based on the value of si, it will be narrowed down, so it will be taken. So now the new value of this is, we will be taking the maximum of the old one and the new one, and upper bound will be taken as the minimum of the old one and the new one. So it will be like we will be taking, like we will be, so we observe that our interval will be narrowed to new and new b. So if it is narrowed or equal, we are like adding this interval into this new m variable. Now the below steps follows until we get the properly padded until we get the message. So the process is like, first we will be checking whether we told that we will be, for one interval cases, we will be following a binary search optimization method, in which you will be limiting the search space of si. So that is done here for one interval case new m, that is length of new m equal to 1. In that case you are finding r is nothing but, it is taken first as twice bsi minus 1 minus 2b by n, and then we are finding the mi's, which you are finding, see here you are calculating again mi based on the si we got, based on this si we are finding mi's. If any of the mi is properly padded, it will be coming out of the loop, and we will be printing the number of iterations and the s value you got. So suppose if it is not the interval is, then number of intervals is not 1, then we will be simply iterating this loop by iterating si from si plus 1 plus 1 plus 1, like that, and we will be printing all the possible si's. So in this case we got an si, and we come out, and when we come out, after coming out, based on the newly found mi, you narrow down the interval of m0 using the same process as I told above. So in here you are actually storing it to new mm. So now you are checking whether this new length is greater than 0. If it is 0, then you are just setting new m equal to new mm, so that you can go in the next loop. But in our in the final case, the length of new m will be equal to 1. So if that is the case, we will be comparing. If it is like final case as in, okay, So in the final case, when there is only one interval, what we do is we just pop out the interval and check whether both the intervals, like the a and the b value, that is popped of, I am getting the intervals in popped, so popped of 0 and popped of 1 is equal. That means it has been converged to a one point, one single point, and that one point will be our message. So I am just printing the message here. Fk popped of 0. Fk is nothing but, Fk is actually used to format the string to print the hex values with 0 padded values. So I'm just using that here. Fk percentage pop will give me the proper hex in the hex format, and and I'm also printing the decoded message, which is calling my decode message function, which I had defined here, which just convert it into my ASCII form. So in here you can see that I'm just checking, like I'm taking two bytes each, and I'm comparing if it is after, and I'm taking it after first 2 bytes, and I'm checking after first 2 bytes if I'm encountering any 0. If I'm encountering any 0, that means my index, like the proper message, my message starts after 0, right? So I'm just taking index as I+1, and that message I'm returning, and I'm just decoding it in hex format here, and I'm just printing it, and I'm just printing my initial message, and I'm decoded initial message. So I am running the code, and my code is python pp.py. So here you can observe that I am getting in each iterations I am getting some value for explode values of r, and I am also printing the values of s, and finally you can see that it has converged to a single point, and that is why we are getting this found message as this, and this was our initial message. So we can see that both are same, and I'm also printing the decoded message Gino. So that is the Bleichenbacher attack. So we had make use of the padding oracle to identify whether our message is properly padded format or not. Like this way we try different different SIs, and that was M0 SIs, and we are narrowing the interval such that it converges to a particular value, and that will be our message. So this was Bleichenbacher attack, and thank you.